Welcome to our training series on Intel's next-generation firmware initiative, the Universal Scalable Firmware, USF. For this session we will dive a bit deeper into the platform orchestration layer. The platform orchestration layer, POL, is aimed to provide guidelines on writing platform code that leverage a scalable Intel firmware support package interface and payload to coordinate the overall platform initialization flow. This layer is the bootloader of the developer's choice and will govern the overall boot flow. Also, this is the layer for the build process infrastructure. Following the next-generation firmware initiative, the Intel system firmware, BIOS, is evolving to be a multi-layer, modular, scalable firmware solution which fulfills all the modern firmware requirements in a super-complex hardware IP-centric world. Let's look at the characteristics of the POL. The platform orchestration layer sits between the SoC abstraction layer, SAL, as abstracted by the Scalable FSP interface, and the payload layer. The platform orchestration layer coordinates the board-specific boot sequence, invoking the SFSP interfaces for any silicon-specific work. The POL produces the interface to launch the payload environment along with industry-standard tables that are an amalgam of silicon and platform, such as SM-BIOS and ACPI. Therefore, the missions of the POL layer are: first, initialize the board by programming board-specific resources and invoking the Intel FSP for SoC and/or XPU-specific resources and, second, invoke payloads for the OS boot environment and possible the XPU and runtime. The POL plays a major role in providing vendor-specific features and mainboard-specific initialization, as distinct from the Intel FSP that is scoped to be SoC-specific. For example, the POL will be the conduit to the Intel FSP interface to 1. Convey policy, 2. Interact for initialization, and 3. Retrieve hardware state information. What are the design principles for the POL? The architectural design of a POL shall follow these principles. For compatibility, POL shall be compliant with the Intel FSP specification, provide the configuration information into the Intel FSP, and retrieve resultant output information from the Intel FSP. For portability, POL will attempt to be as SoC independent as possible and allow for source-level compatibility between different open-source platform code frameworks such as EDK2, Coreboot, Orboot, and Uboot. The OS boot-specific code is abstracted via payloads. For determinism and simplicity, POL should abstract SoC initialization through FSP interfaces and have a simple boot flow. The POL is considered as the layer for platform code and will typically be the build environment for building a platform binary image, and in addition, orchestrate the boot flow. On the left show the boot flow stages of many bootloaders segregated into different levels of initialization: early, late, and then runtime. For early, typically the bootloader will consume the reset vector and start to interface with the Intel FSP for the silicon initialization. For late, the bootloader will do more robust initialization in preparation for calling the universal payload. For runtime, this can be a combination of initialization with the bootloader and the universal payload with the goal of setting up data structures and interfaces passed on to the OS. One goal of the USF spec is the collaboration in the reuse and sharing of code. For example, take ASL code. If there is ASL code for a given board, why shouldn't a system firmware developer have the opportunity to reuse the same ACPI source language, ASL code for different bootloaders with the same board? Think of it as board.asl for that given system board. Next, let's look at a few examples of the platform orchestration layer, POL. There are a few examples such as Tiano Core EDK2, Slim Bootloader, and Coreboot. All of these POL bootloader examples interface with the Intel FSP API specification, as defined in the Intel FSP 2.3 spec. Then on the other end, POL interfaces with the universal payload, invoking the universal payload entry point after providing board initialization. Shown here is the UEFI EDK2 well-known boot flow diagram. The chart shows the bootloader starts at the reset vector in the security stage, sec, where it will start interfacing with the FSP. In this case, we see that the sec will call into FSP-T, where it will initialize the temporary memory stack and data areas. The EDK2 initialization continues in the PEI phase, continuing to call into the FSP interface for the memory initialization, FSP-M, and silicon initialization, FSP-S. There may be callbacks into the FSP in the Dixie phase, where there may be registers that need certain values before launching the OS. This is the current way UEFI EDK2 platforms will interface with the Intel FSP. So now let's look at the same boot flow chart with USF. You will still have the interfaces to FSP as before, and this interface will work the same way as the FSP specification. However, the difference for USF is that instead of calling the huge Dixie phase, instead with the USF implementation there will be a call to the entry point of the universal payload passing the hand-off blocks, HOB, as an input to the universal payload. The universal payload will prepare for the runtime interfaces required by the OS. In addition, there may be other EDK2 drivers required for the runtime interface. In this case, we see EDK2 platform-specific payload interfacing via callbacks from the universal payload. This is the same figure, Figure 11, illustrated in the USF specification in the Platform Orchestration Layer section for the UEFI EDK2 bootloader implementation. This simplified figure reflects the chart on the previous slide. And here's another view of how a single UEFI payload could be used to potentially be delivered in binary or derived from source, as shown in the blue box. This model could be used across the various bootloaders leveraged with a EDK2 style bootloader. The diagram shows the data flow of the HOBs from the EDK2 bootloader to the universal payload. In order to separate modules in different boot stages, EDK2 has standardized the firmware layout using UEFI firmware volumes. Platform initialization specification from the UEFI org has the firmware volume specification in Volume 3 of the PI spec. The basic storage repository for data and code is the firmware volume. Each firmware volume is organized into a file system with attributes. One or more firmware file sections files are combined into a firmware volume. The flash device may contain one or more firmware volumes, and in fact, will contain many. The EDK2 FDF file controls the layout as part of the build process. Shown here is an example of the EDK2 integrated firmware image, IFWI, layout. This example is following the minimum platform architecture specification using different UEFI firmware volumes for the progress of the bootloader boot flow. FSP is shown as 3 firmware volumes according to the current FSP 2.3 spec. Also notice that many firmware volumes are part of the IFWI as well as areas that are not UEFI firmware volumes. For example, the flash descriptor is not a UEFI firmware volume. Next is the Slim bootloader example. The Slim bootloader is a modular design approach adopted by the Internet of Things groups to make the system platform firmware more modular by providing a streamlined approach for hardware initialization, then launching a payload to boot the OS. Slim bootloader provides a minimal firmware footprint for IoT platforms and has scalable designs. Slim bootloader has the approach of platform initialization combined with the Intel FSP for the silicon and memory initialization, where the platform is responsible for initializing the settings for GPIOs, ACPI, etc. The payload is flexible and can be the user's choice to meet special needs. Slim Boot takes a linear staged boot approach to initialize the platform. Shown here are the different stages for the different levels of the boot flow, Stage 1A, 1B, and Stage 2. As shown also in the diagram, in each stage, Slim Boot uses the Intel FSP APIs to initialize the silicon and utilizes static library interfaces to initialize the board. These static library interfaces are aligned with EDK2-based library implementations to abstract the board initialization APIs. For example, similar base library implementations are used in the EDK2 bootloader to initialize PCIe, ACPI, etc. Also shown is a high-level list of the initialization occurring at each of the Slim bootloader stages. As previously mentioned, Slim Boot utilizes static library classes to abstract the API interfaces for platform initialization. These libraries are written in C, so that it can easily be shared between different boot solutions. For example, many base library instances in EDK2 MDE package are directly leveraged by Slim Boot. Many other libraries, such as SoC access libraries and feature libraries, are also ported from corresponding EDK2 libraries through removing UEFI-specific dependencies. In addition, ACPI ASL files are also borrowed from EDK2 directly. These shareable libraries and files make it easier to quickly enable a platform using the boot solution of a developer's choice. Here is the Slim bootloader flash image layout showing support for redundancy. Their FSP, as shown, is also part of the redundancy as integrated with the different stages in the Slim bootloader flash device layout. The next example is CoreBoot. CoreBoot is a project to develop open-source boot firmware for various architectures. Its design philosophy is to do the bare minimum necessary to ensure that hardware is usable and then pass control to a payload. CoreBoot has a well-defined set of stages. They are boot block, ROM stage, post-car, and RAM stage. These stages will make calls into the various Intel FSP interfaces as shown in the diagram. Today in FSP API mode, CoreBoot also has its payload interface. Some examples of CoreBoot payloads are Depth Charge, Linux Boot, UEFI Tiano Core, and CBIOS. But with USF, this can easily become the universal payload. CoreBoot principles include performance, simplicity, security, and open source. CoreBoot is a first-class example of a POL today. Here's an example and details on how CoreBoot interacts with Intel FSP 2.3. Starting with the power on of a platform system, all the power rails and hardware are initialized until the processor starts fetching code at the reset vector. Here, as shown at the top right, CoreBoot takes control of the reset vector. Then it interacts with the FSP fixed interfaces through the FSP-T, -M and -S, and then through the various FSP notifications or callbacks. Then, of course, once the finalization of the silicon interaction with RAM stage is complete, CoreBoot can call the payload which will then load the OS. Let's break down the steps for the interaction with the Intel FSP. First, CoreBoot owns the reset vector and contains the real mode 16-bit reset vector handler code. Optionally, CoreBoot can call FSP-T for car, cache as RAM, set up and create a stack. Next, CoreBoot is required to fill in the required updatable product data, UPDs, before calling FSPM for memory init. Then, on exit of FSPM, CoreBoot needs to tear down car and do the required silicon programming including filling up UPDs for FSPS before calling FSPS to initialize the chipset. Optionally, the bootloader enables multi-phase silicon initialization by setting the FSP multi-phase enable switch to a non-zero value. On exit of FSPS, Core boot will perform PCI enumeration and resource allocation. Next, the bootloader calls the get FSP multiphase SINIT API to discover the number of phases of silicon initialization phases supported by the bootloader. Then, the bootloader must call the FSP multiphase SINIT API with the discovered number of phases returned previously by the get call. Bootloader may perform board-specific code in between each phase as needed. The number of phases, what is done during each phase, and anything the bootloader may need to do in between phases shall be described in the FSP integration guide. Core boot calls notify phase at proper stages before handing over to the payload. Here is the core boot integrated firmware image layout that shows the core boot file system components that would be part of the flash device layout. On the right, the different boot flow stages are shown and also indicate if firmware is executing from the flash, read-only memory, or system memory, read-write memory. Finally, UFS allows for a world where there are various compositions of the firmware stack. One future example that could be supported in USF is OR-boot. OR-boot is a fork from core boot but written in Rust language instead of C. Going forward, Rust is a language with public safety in mind. So to that end, the OR-boot project is another great POL to explore. It makes sense to use OR-boot with USF using the universal payload since OR-boot already has some of the FSP interfaces. Some exploration is being done already with a firmware stack based on Rust, starting with virtual firmware, which is not bare metal. There are links to these examples on this slide. One goal of USF is to share interfaces such as ASL, board code, or to have interoperability between payloads, not just the C-based, SlimBoot, Core Boot, or EDK2, but even embrace the emerging Rust bootloader community. In summary, the USF platform orchestration layer offers several opportunities to include a bootloader of a developer's choice. It can be simple to complex. The POL is the bootloader that governs the boot flow and orchestrates the build process. This concludes our dive into the USF platform orchestration layer. For our next session we will take a look at the Intel FSP and Scalable FSP interface.